Hello students, welcome to my channel Engineering Education. Please subscribe my channel. Thank you. In this video we are going to discuss example 10.1 from chapter number 10, Nozzles and Jet Propulsion, from the book Applied Thermodynamics by T.D. Stopp and McCranky. The statement is air at 8.6 bar and 190 degrees centigrade expands at the rate of 4.5 kg per second through a convergent-divergent nozzle into a space at 1.03 bar. Assuming that the inlet velocity is negligible, calculate the throat and the exit cross-sectional areas of the nozzle. So first of all, we will extract some information given in this statement. First of all, we will write the given pressure at the inlet, that is P1, and it is 8.6 bar. Temperature, that is 190 degrees centigrade, T1, 190 degrees centigrade, and the mass flow rate is 4.5 kilogram per second. The nozzle is convergent-divergent and it is shown over here. This is the inlet conditions. P1 is 8.6 bar, T1 is 190 degrees centigrade, and the inlet velocity, that is C1, is negligible and it has value 0 meter per second. We are required to find two areas in this. One is the cross-sectional area at the throat, that is AC, and second we have to find the cross-sectional area at exit. So basically, if I highlight these areas in the sketch, this is the cross-sectional area at throat and this is the exit area. Now, to start the solution of this example, first of all, we should know about the formula or equation or expression which will be used for calculation of cross-sectional area. So the equation or expression which will be used in the calculation of cross-sectional area, that is continuity equation. And continuity equation, if I highlight the parameters of the continuity equation, those are area, velocity, mass flow rate, and specific volume. So for finding the critical or throat area, we can write that AC is equal to m dot small vc divided by cc. So we should know about the values of these parameters. Let's suppose this is equation A. So in this expression we have given mass flow rate and it is 4.5 kilogram per second, Vc and Cc. This is known and these two parameters are unknown. Again, if we are interested to find the exit area, for that we will modify this expression again, and that is AE is equal to, simply C will be replaced by E exit or cross section 2. So this is the basically the expression used for cross-sectional area calculation. M dot V2 by C2. Let's suppose this is expression B. It is also mentioned in the convergent-divergent nozzle sketch that inlet is designated with 1, mid section or throat is designated with C, and the exit of the nozzle is designated with 2. Now to find these values VC, CC, V2 and C2, for that we will need some other supporting parameters and relationships. So first of all, we will find the critical pressure at throat. For that, using the expression PC by P1 is equal to 2 by gamma plus 1 power gamma by gamma minus 1, where in this case for air the value of gamma is 1.4. Because this is air expands in this nozzle, so gamma value is 1.4. Now if we put the value of gamma in this expression, we get PC by P1 is equal to 0.5283. So this is the critical pressure ratio PC by P1, and it is 0.5283. Now to find the value of PC, for that we will multiply P1 with this ratio. So P1 is 8.6 bar given, so the value of PC comes out 4.543 bar. Further, to find the temperature TC or temperature at throat, we have relationship TC by T1 is equal to 2 by gamma plus 1. So when we put the value for gamma is 1.4 and simplify it, we get 1 over 1.2. Now T1 is 190 degrees centigrade, so we will convert first it into Kelvin. So adding 273 with 190 and simplifying it, we get 385.8 Kelvin. Now it's very easy to find the value of specific volume at throat using ideal gas equation or perfect gas equation. We have a relationship which is PV is equal to RT. This is the general expression of perfect gas equation. So we can also write it for the throat area, that PC VC is equal to RTC. In this expression, R is the particular gas constant, R specific gas constant, and its value for air is 287 joule per kilogram per Kelvin. So putting the values, R is 287, TC is calculated above 385.8, and PC is also calculated, it is 4.543. Multiplying 10 raised to power 5 factor with the pressure value, because the value of pressure is given in the bar, so we will convert it to Pascal. So that's why 10 raised to power 5 is multiplied with this. Finally we get the value of specific volume at throat, which is 0.244 cubic meter per kilogram. Now further, to find the velocity at the throat, for that we have two expressions to calculate it. First, under root gamma RTC. Gamma is given 1.4, R is given 287, TC is the throat temperature and it is 385.8. so simplifying this, we get 393.7 meter per second. Also using another expression, CC is equal to under root 2 into H1 minus Hc, where H1 is the enthalpy at the inlet of the nozzle and Hc is the enthalpy at the throat. So further specific enthalpy in case of perfect gas, it is equal to CpT. So for state 1 and at the state C, which is the throat, again expanding it for in terms of temperatures, we get 2 Cp into T1 minus Tc. T1 is given, Tc is calculated. So 2 multiplied by 1.005, this is the value of specific heat at constant pressure for air, and multiplied by 10 to the power 3, converting kilojoule into simply joule. T1 is 463 and Tc is 385.8. So again we get the same value as calculated above. So in this case, either this equation will be used for calculation of Cc or this equation. Now to find the area at the throat using the equation of continuity, that is AC is equal to m dot Vc by Cc. So putting these values as calculated, we have m dot 4.5 and Vc is 0.244 cubic meter per kilogram and Cc is 393.7 meter per second. So this is the value 0.00279 square meter, or if we convert it to square millimeter, it will be 2790 square millimeter. Further again repeating these calculations for the inlet, for the exit, so it is T1 by T2 is equal to P1 by P2 power gamma minus 1 by gamma. So P1 is 8.6 and P2 is 1.03. So when we put these values in this expression, we get T2 is equal to 463 by 1.834. So the value of T2 is 252.5 Kelvin. Further, to find the specific volume at exit, for that again using the perfect gas equation, in this case it will become P2 V2 is equal to R T2. In this case V2 is unknown, so R is 287, T2 is 252.5 as calculated, P2 is 1.03. Converting it to Pascal, we get 0.7036 cubic meter per kilogram, which is the specific volume at the exit of the nozzle. Further, to find the value of velocity at exit C2 using again the same expression while modifying for the inlet and exit conditions, 2 into H1 minus H2, where H1 is the enthalpy at the inlet and H2 is the enthalpy at the exit. Again expanding in terms of temperature, we can write it like this, 2 Cp into T1 minus T2. Now putting the values under the root 2 multiplied by 1.005, which is the value of Cp. Again converting kilojoule into joule, we will multiply 10 to the power 3. T1 is 463 and T2 is 252.5. So when we simplify this, C2 value comes out 650.5 meter per second. Now using the continuity equation to find the cross-sectional area at exit, A2 is equal to m dot V2 by C2. So m dot is 4.5 kilogram per second, V2 is 0.7036 cubic meter per kilogram and C2 is 650.5 meter per second. Simplifying this, we get 0.00487 square meter. Also, if we represent it in square millimeter, we can also write it like this: 4870 square millimeter. So this is all about the discussion of example 10.1 from chapter number 10, book Applied Thermodynamics by T.D. Stapp and McConkie. So if you like my videos, please subscribe my channel. Thank you.